In this lecture, I want to discuss two different approaches to transfer learning, both of which we will cover in the subsequent coding lectures. The main issue I want to cover is this. Imagine that the body of our neural network is very large, let's say hundreds of layers. The head, as discussed previously, can just be a single logistic regression dense layer. The issue is, even though we are not training any of the weights in the body, it still takes time to compute and output prediction. Just imagine a really big, long, nested function. At each of these layers, we have to do a convolution, which is faster than matrix multiplication, but still can take a non-trivial amount of time. Imagine this computation in two parts. In order to calculate the output prediction, we first calculate a feature vector z, using the body of the neural network. Then, in order to calculate the output, we take z and pass it through a logistic regression. My issue is, the first part, calculating z, is what takes a long time. Now consider that our gradient descent loop works as follows. We loop through each batch of data. For each batch, we calculate the output prediction y hat. Then we calculate the gradient of the error with respect to the logistic regression parameters w and b. Then we update a w and b using those gradients. The thing we want to think about is this. Does the calculation of z ever actually change? Since z is the output of the VGG network after passing in our input data, it doesn't make sense to put this inside our loop, because it's going to be the same every time. Remember, the VGG weights are not going to be trained. So here's what I propose. Remember my rule, all data is the same. The idea is, before we even begin training, let's convert our image data into a tabular matrix of feature vectors z. Then, all we need to do is run logistic regression on z without ever looking at the VGG network again. By doing this, we can avoid having to pass our data through any pre-trained network, which can take a lot of time if it has a lot of parameters. Alright, so there's a problem with what I just proposed. What is it? Well, remember that when we create our image data generator, it gives us the option to do data augmentation. With data augmentation, every time we loop over the dataset, the generator modifies the original images just a little bit to help our neural network generalize better. Of course, if x is different on every iteration of the loop, then z will also be different on every iteration of the loop. In this case, we cannot pre-compute z before the training loop begins. The only time it makes sense to do that is if we don't care about doing data augmentation. So these are the two approaches. Approach number one will be to use the image data generator with data augmentation. This means we have to put the entire CNN computation inside the training loop. Approach number two will be to pre-compute the feature vector z on the original data x without data augmentation. This means that, after transforming the data, all we need to do is train a logistic regression model. There are pros and cons to each approach. Let's list them out. As discussed earlier, when we do use data augmentation, that means we have to recompute the features for every batch we see. This is slow, especially if you have a large network. Yes, it's faster than training the entire network, but still slower than only training a logistic regression. On the other hand, data augmentation may help your model generalize better. Without data augmentation, it's basically the opposite situation. You can pre-compute the features before training, which will save you a lot of time. Training logistic regression is extremely fast. Yet, this also means that you cannot use data augmentation, which may cause your model to perform suboptimally. However, it's always worth trying both to see which method gives you the best results for your specific dataset.